So, paper title is Unsupervised Learning of Legal Transformer by Embedding Ordinary Differential Equations. So first, I want to talk about humans' mental transformation abilities. We can mentally transform imaginary objects in mind, and this operation is called mental rotations. It was experimentally proven that time to recognize these objects as the same is proportional to the angular difference, which indicate that we have mental transformer and that we are rotating them by a small amount iteratively. And this mental simulation ability is something we acquire with development, because children 18 months and younger can readily solve a task which requires mental simulation abilities. Next, I want to talk about the related works that can acquire transformation in an unsupervised way. Traditionally, transformation recognition based on V-group theory is researched by many researchers, and recently deep learning models to learn representations are devised. Someone would think representation learning models like this is different from transformation recognition models, but in a sense that learn latent codes corresponds to certain transformations such as translation or rotation. These models are very related to transformation recognition models. The problem that these models have in common is that these models require a lot of training datasets, usually more than 1,000. And my research purpose is to acquire transformation from far much fewer number of images by assuming some algebraic structure in the model. Briefly, I'm going to explain the formulation of transformation recognition in Lie group theory. It is known that the transformation to certain pattern F generally consists of a combination of several basic transformations, and these basic transformations should meet the following conditions. First, there should be identity element, and second, for each element in the group, there should be inverse element, and lastly, associativity should stand. And then recognizing transformation T of K can be formulated to determine the transformation quantity lambda and type of transformation just from images before and after transformations. As a transformation model, having these axiom properties is important, and we find out that ordinary differential dynamics, differential equation dynamics, ODE dynamics in short, always meet these properties. So for example, we take this ODE, and if we consider the input vector xbef, ybef as initial values, and if we consider integration time as transformation quantity lambda, then we can get the output after transformation by variable lambda by computing these integral computations. These functions always meet the axiom of groups. Here we propose the ODE embedded pointwise transformer. In this model, objects are considered to be a collection of tiny points, and each pixel is transferred to another position based on current coordinate information. And destination of each pixel is determined by neural ODE, which is a neural network embedded with ODE dynamics. I'm going to give a brief explanation about the mechanism of how each pixel is transferred. First of all, we need to understand how to express the continuous location in the image. Please consider this array as one image, and activating position 2 is setting the theta2 as 1 and setting all other parameters as 0, and activating position 3 is setting like this. The question is, how should we express activating continuous locations such as 2.5? To express continuous location, we activate the neighborhood pixels as well. And if all parameters follow this equation, we can express activation of continuous locations as is shown in this table. we can simply extend this approach to 2D image by multiplying X and Y components like this. And this vector means information of a pixel. P is the activation value of the pixel, and XF and YF is the activation position computed by neural ORI from the previous position. We generate a map in which target position is activated by P just from these vectors. And this it depicts the end-to-end flow of pointwise transformations. So for each pixel, we compute target coordinates XF, YF from current coordinates XBIF and YBIF. And from each pixels, we generate maps as is shown in the previous slides. If we take some of all these maps, we can obtain the output of these transformers. There's one more important practical trick. If we use herd activation function, and if the output position is far off the gradient of objective, in this case, the area of overlap will be 0. So to avoid gradient loss, we use a soft activation function. And from now, I'm going to talk about experiments and its result. The purpose of experiment is to acquire transformation just from the sequence in which the cube is moving to the right. There are only 8 sequences in the total, and each sequence has 8 images. This is much fewer than conventional models. Just from these sequences, we want to determine the transformer that translates anything. We build this learning architecture. First, we randomly initialize the parameters of transformers and transformation quantities, these parameters. And this model will generate the estimated images of mid states at the depths of estimated lambdas. And we take the reconstruction losses between the generated images and given images. And all parameters are updated to minimize the sum of the reconstruction losses. We use the masked MSE mean square errors to compute reconstruction losses. We cannot use normal MSE loss because our model is a model that transfers pixels to another positions, and most of the times in MSE, normal MSE losses hinders the pixels to approach the target positions, as is written here. So as a result, we obtain shape invariant translation transformer. Our obtained transformer was applicable to unseen objects. These objects, shaped bird, cube, oval, were not included in the datasets, but our model was able to transform them successfully. Although there were no inverse transformation in the datasets, but our model was able to apply inverse transformation by setting transformation quantity as negative. As for estimated lambdas, we plot both estimated lambdas and ground truth values. And from this figure, it can be said that estimated lambdas are close enough to ground truth values. This model can find other type of geometric transformations. If we feed the rotation sequence, this model can be the rotation transformer. And if we feed the sequence in which a cube is expanding, we can obtain the scaling transformer. This is a visualization of field that each land transformer forms. Always in these figures show the direction and power of the transformation applied to each point in the images. From these results, it can be said that transformations in sequences were properly determined. So I want to conclude my speech. We propose a novel approach to determine transformation from successive field images. The model we devise is embedded with ODE dynamics to meet algebraic properties of Lie group and we acquire the shape invariant geometrical transformer by training the model to reconstruct a sequence. But there are some limitations, as such that model can only deal with single transformation, and these are problems to be tackled in near future. Other future works would be dealing with multiple geometrical transformations or running a 3D geometrical transformation from 2D images. These are references. Thanks for watching.